Here are the equations that we're going to use to solve problems having to do with the half-life and decay of a radioactive sample. It doesn't matter what kind of decay is going on here. What matters is how much of the sample there is and the half-life of the specific sample. N stands for the amount of the sample now, and that amount can be in grams or milligrams or moles or just about any amount as long as the N naught is the same amount. So the N naught is the original amount of the sample, and it just has to have the same units as the N. K stands for rate constant, and that's going to be in per seconds or per days or per years. It's the inverse of whatever the half-life has as a unit. The half-life, T1 half, is the amount of time that it takes for half of the sample to decay, and it's going to be measured in seconds, minutes, days, months, years, etc. The T actually stands for the time period that we're allowing this to decay, or that it has been decaying, and it can be in units of time too. In this problem, it is telling us that the half-life of thallium-201 is 72.9 hours, so we know T1 half is 72.9 hours. It wants us to find out how much time is required for the activity of a sample to fall to 17.6% its original value. So we know that our amount is going to be 17.6%, and since percents are out of 100, we can call our N what it's at now, 17.6, and our N naught, 100. We are going to need, in order to do this equation, a K. To find K, we use 0.693 divided by the half-life, so 72.9. You get 0.009506. The units for that, because what we put in is hours, this would be decays per hour. That's going to be our K. So now we can plug this into this equation. And when you solve this, you get a T of 183 hours. All right, this problem tells us that the half-life is 44.5 days. From that, we can calculate the K. The K ends up to be 0.01577 per day. It tells us that we begin with 45.3 milligrams, so the N naught, original amount, is 45.3 milligrams. It asks what mass remains, so we're trying to find N after a time period of 73.9 days. So we're going to plug it into this equation. This equals negative 1.151, and then to get rid of this ln, you have to do the inverse. So you have to type second ln, and then what it's going to put in your calculator is e to the something, and then you put in negative 1.151 and hit enter, and then it will give you a number here, which you then can multiply by 45.3, and you will get 14.3 milligrams. In this problem, it's asking us to find the half-life. In order to do that, we're going to have to solve for K, because our equation has half-life and it needs rate constant. It tells us that the time is 167 days and that our sample is going to be 7.44% of its original value. Again, since we're dealing with percent, let's make the original value a 100 and the current value 7.44. And these units could be grams or milligrams, whatever we want them to be. We solve for K, and we get 0.01556, and that is decays per day. And then we plug that into this equation. We solve for T1 half. And we get a half-life of 44.5 days. Okay, this is the last problem, but it's quite a bit different than the others. In this one, you need to understand that the amount of mass that protons and neutrons have when they are not in a nucleus is greater than the amount of mass that they have when they are in a nucleus, which means that they can release energy by forming a nucleus. And since all things in nature want to exist at a state where less energy is required. That is why nuclei form. So in this case, we have 29 protons. Each of those protons has a mass of 1.00783. So we can take 29 times 1.00783 and add it to the number of neutrons. Now the number of neutrons is 63 minus 24, which is 34. It's also telling us in this balanced nuclear equation that there are 34 neutrons. Each neutron has a mass of 1.00867, and when we add that up we get 63.52185, and those are molar masses, so that's grams per mole. Now this is the amount of mass that all of these protons and neutrons have before they are combined into a nucleus. This number is the mass of a copper-63 isotope, and this is the mass that it has after it's formed into a nucleus. So we can calculate something called the mass deficit by taking the mass the protons and neutrons have before minus the mass they have after. And that gives us a mass deficit of 0.59205 grams per mole. That's called a mass deficit. Now this equation, E equals mc squared, can convert mass into energy. So energy is in joules, the mass needs to be in kilograms. We have a mass in grams, so we'll have to convert. And then C stands for the speed of light, which is 3 times 10 to the 8th meters per second. So we're going to plug into this equation this number of grams, and we're going to drop the moles for a minute. We'll put that back on after we do this calculation. We're going to change this to kilograms by sliding 3 places to the left. So 0.00059205, that's the m. C squared, we're going to put 3e8 squared into our calculator, and when we solve for that we get 5.328 times 10 to the 13th joules per mole. The per mole came from right here. Now the answer wants kilojoules per mole, so we have to convert joules to kilojoules. 1,000 joules are in 1 kilojoule. Joules cancel, so we multiply by 1,000, and we end up with 5.33 times 10 to the 10th kilojoules per mole for our binding energy.